Okay, let's start. Today we're going to talk about the matrix of the linear transformation. Before starting, we have two notifications. The first one is the homework. Actually, this is the first homework of this course. So, first of all, the due date of this homework is the April 19, Sunday until midnight. Okay, so you should submit this homework through the Blackboard website. I guess all of you having experience on Blackboard, so you can easily download the homework in the Blackboard, and then you can submit your homework on the Blackboard website. Okay, so there is the problem set in our textbook. Okay, so please be careful to use the 5 edition in our textbook. There are numbers of our homework. So from the chapter 1.1 through the chapter 1 through the 1.9. So today we're going to deal with this section or this chapter, but we already talk about the whole of these chapters. So please try to solve these problems yourself. Okay. There are some instructions. First of all, you must submit the photographed or the scanned file electrically in Blackboard. Okay. So you can solve the problem by hand or type the solution through some kinds of the application or the program, something like the Word, Microsoft Word, or the PDF, something like that. You can fully use the way you are preparing. Okay, then there are some late policy. So there will be the 25% of per day late. Okay. And the homework should be written in English. Okay. And please do not copy your friend's one. Okay. And please start your homework as soon as possible, because I already uploaded the homework in our Blackboard website. So I guess we have 10 days until due date, so please start your homework as soon as possible. Okay, so this is the one notification. Another is related to the midterm of this course. As you know, in this semester there were online courses until the 1st of May, right? Due to some coronavirus things. So I decide we cannot have a midterm exam because in this course there are 100 people or 100 students. So I decide that it will be really difficult, or it will be really dangerous to take a midterm exam. So you should keep in mind there is no midterm exam in this semester. So I will announce the new grading policy without the midterm exam. Okay. So that's why there are many homework in this homework 1. So please try to solve this kind of homework by yourself. Okay, so this is the notification. Okay, so let's start today's lecture. So before starting, let's go back to our previous slide. In the last lecture, we were talking about the introduction of the linear transformation, right? So what was the linear transformation? So linear transformation is related to Ax equals B, right? So we want to think of the matrix A as an object that acts on the vector X, okay? So the linear transformation is a mapping a vector X by the matrix A, something like that. So we call this equation as a matrix linear transformation, okay? So there are some terminology related to the transformation or the linear transformation. So if the transformation T is from the Rn to the Rm, so we can say that the set Rn is the domain of the T, and we can say that Rm is the codomain of the transformation T, okay? So this is the visualization of the domain and codomain, okay? And then there are two more things. The first one is image, second one is range. The image of the X is the output of the transformation of the input X. So this is the image. And the range of the T means that the set of the whole images or whole output through the transformation T of X. Okay, so this is the definition of the domain, codomain, and image and range. Okay, here is another terminology related to matrix. Rather than using the T over X, we can describe the T over X as A times X, where A is the n by n matrix. So in this case, domain, codomain, and range can be defined in the matrix formulation. So there was some examples, right? And yeah, something like that, So yeah, we were talking about the shear transformation, right? And yeah, there are two kinds of property of the linear transformation. First one is the T of the u plus v is equal to T plus tv. The another second one is the T cu is equal to C T of u. So this property easily proved by using some kinds of the operation of the vector addition or scalar multiplication. Today we will use this property to derive another terminology. Okay, and there are additional properties such as the T0 is equal to 0 and TCU plus TV is equal to CTU plus TTV. Okay, and this last property can be extended in a generalized manner, something like that. So here, so this is called the superposition principle in engineering and physics field. So yeah, so it was the last lecture. Today we will move on to the matrix transformation. Okay, before starting, there is the two concepts. First one is the elementary vector. So what is the elementary vector? Okay, let's think about the identity matrix first. What was the identity matrix? What was that? Identity matrix means that something like this, right? So it has some kind of the shape like this, right? This is identity matrix. Why do we need the identity matrix? Because the identity matrix some desirable property such that identity matrix times some kind of vector will be the vector itself. Okay, so this is a very important property that needs identity matrix. Okay, so first of all, if we have the identity matrix 2 called I2, the shape of the identity matrix looks like that. So in this case, let's say there is a two column, right? This one and this one, right? So in this case, we can define the elementary vector E1 and E2, something like that. What I mean is in the 2D space, the matrix vector E1 will be looks like that, and matrix E2 looks like that. Okay, so this is the elementary vector. Why do we need the elementary vectors E1 and E2? We can represent the whole point in the 2D space by using this elementary matrix E1 and E2. So this is the very important property of the elementary vector. What about the I3? I3 also have the three columns, so we can define the E1, E2, E3, something like that, and it will be looks like the let's say this is E1, E2, and this is E3. So this is the definition of the elementary vector. And then with these elementary vectors, how can we write some arbitrary vector x is equal to x1, x2, and x3 in R3 space as a linear combination? How can we do that? First of all, we already know the I3 times x is equals to x itself, right? So it means that we can write this vector something like that, right? Then what is the I3? I3 looks like this, right? So with this vector as a coefficient of this column vector, right? We can represent this one something like x1 times this first column, x2 times the second column, x3 times third column, right? So in this case, this is the E1, E2, E3. So it means that this is the x1 is the in this case x1 times elementary vector 1 plus x2 times element vector 2 plus x3 times elementary vector 3. So we can represent the arbitrary matrix X as in terms of the elementary vectors. Okay, so yeah, these are simple introduction of the elementary vector. Okay, let's move on. So here are some example. Suppose transformation T is a linear transformation from R2 and R3, R2 to R2, such that transformation vector 1 over 0 is the 2, negative 1, and transformation 0, 1 is going to be 0, 1, right? So what is that? This is the elementary vector 1 and this is the elementary vector 2, right? Then find the formula for the images of the arbitrary vector x in the R2 space. Okay, first of all, we already know the arbitrary vector x is going to be x1 times the 1, 0 plus x2 times 0, 1 as a elementary vector 1 and element vector 2, like that. Then how can you do that? And okay, so we want to find the formula of the t over x, and it can be represent something like that, right? From this property. Then because this transformation is linear transformation, so there is some addition and multiplication property here from here to here, right? So we can represent this formulation something like that. Okay. So from the definition, we can represent this one as a 2 comma negative 1, and this one can be represented 0 comma 1. So in other words, okay, we can say that this is the column vector, and this is the another column vector, and this is the coefficient, right? So you can represent this formulation represents something like the x1, x2 with the the matrix consisting of the 2 column vectors, something like that. So we can say that. So this transformation is the A times vector x. Okay. So this is the examples of the linear transformation. Okay, here's another example. Okay, the columns of the identity matrix 2, this one, E1 and E2, right? So then suppose the T is the linear transformation from the R2 and R3, then first of all, what is the size of the matrix relevant to the transformation T? What is that? 2 by 3, right? Right? Because in this case, the input vector x should be in the R2 space and the output should be in the R3 space. So the transformation matrix should be 2 by 3. So anyway, so let's say the T elementary 1 is equal to something like this, and transformation of the elementary vector 2 is something like that. So with no additional information, find the formula for the image of an arbitrary vector x in R2 space. So what is the image? The output, right? Output of the transformation of the input x, right? So yeah, let's do that. Okay. Yeah, here. So first of all, the input vector x can be represented something like that, and the transformation of x will be looks like that. And what was that? What was the transformation elementary vector 1? See here, was that, right? And what was that? See here, right? So in this formulation, we can write the first element, this first element, as x1 times 5 plus x2 times negative 3, right? Right? What about the second one? x1 times negative 7 plus x2 times 8, not like that. So in other words, we can represent the T of x as this vector form, right? So in a matrix vector multiplication form introduced in the last lecture, we can write this transformation as a TE1, TE2 with the arbitrary vector x, right? From this one, right? So what does it mean? So it will be the some arbitrary matrix A, and it will be the x. So So we can say that the transformation of x, vector x, is going to be equal to the a times x. Okay. Okay. So from this example, we have a new theorem, something like that. So okay, let's linear transformation T Rn to Rm be a linear transformation, then there exists a unique matrix such that transformation of x is equal to matrix A times x for whole vector x in the Rn space. What does it mean? In other words, the matrix A is the m by m matrix, right? Because of this one, right? Then whose jth column is the vector T Ej, right? Where Ej is the jth columns of the identity matrix or the elementary vector in Rn space. Then we can represent this matrix A as a combination or the set of the T elementary vector 1 through the T elementary vector n, right? Right, this one, right? So here the matrix A is called the standard matrix for the linear transformation T. Okay, so this is the theorem. Okay, how can I prove? Actually, we already proved here, right? So I'm going to generalize that solution in the in space. Okay. Okay, let's say arbitrary vector x in the our n space. We can represent x something like that, right? So in consists of the e1 through the en. Then we can represent this formulation, something like that, right? So what is that? This is the linear combination of the column vectors of the identity matrix In, right? So, and then because the transformation is the linear transformation, so Tx is going to be the T like that, and we can decompose this one looks like that, right? So from the definition here we can make a new vector, a new matrix A here with the arbitrary vector x, right? So finally the transformation Tx will be is equal to matrix times vector x. So this is the matrix of the linear transformation. Okay, here's some examples. So first of all, find the standard matrix F A for the transformation T from R2 to R2 given by Tx is going to be R3x for any vector x in the R2 space. Okay, so here we can say that Te1 is equal to 3e1, so it will be 3, 0, and Te2 is going to be 0, 3. So what is the matrix A? What is that? This one, right? So it will be something like that. So this is the definition of the standard what's that? Yeah, standard matrix. Okay. Okay, there are another definition. Today we're going to talk about the two definitions. The first one is the on-to. Second one is the one-to-one. It's okay. Let me show you the first one first. Okay, the mapping or the function t from Rn space to the Rm space is said to be onto Rm if each B in the Rm space, the codomain space, is the image of the at least one X in Rm. What does it mean? What does it mean? Okay, please see the left images. Okay, from the domain, from the input space. In this case, the input space is Rn space, right? By using the transformation, we can transform the arbitrary vector x in Rn space to the some vector in the output space or the codomain space, right? In this case, in the Rm space, right? Right? So what does it mean of the onto? So if the range of the transformation T is not equal to the Rm space, it is called T is not onto Rm. What does it mean? Okay, in the Rm space there are some value which that are not containing in the range space. It means that it cannot at this point cannot be generated by transformation T on any vector x, right? And there are some other case, something like that, something like that, something like that, right? So these values cannot be mapped to the domain space, okay? So this is the case of the not onto Rm. What about the right hand side? As you can see here, by using the sum transformation T, the range of the output of the transformation, this transformation is exactly same to the Rm space. What does it mean? Any point in the Rm space can be derived from the domain or input space. It doesn't matter this point are mapped to the one-to-one or not, right? It doesn't matter here because this concept will be discussed in the next slide. But here, whole possible point in the Rm space can be derived from the domain X. So in this case, the transformation T said to be onto Rm. Okay. This concept equivalently that the T is onto Rm when the range of the T is over the codomain Rm, like this. Okay, so in other words, does T map the Rn onto the Rm is related to the existence question. Okay, so what does it mean? In this case, the solution is the always exist, right? But what about this? For some point, there is no solution, right? There is no vector x that satisfies the ax equals b, right? Let's say this is x, this is b. So in this case, if we want to solve the ax equals b, there is no solution, right? Because any vector x cannot be mapped to this arbitrary point b. So in this case there is no solution. So the concept of the onto is related to the existence question. Okay. The second definition is the one-to-one. Okay, here are definition. The mapping T from Rn to the Rm is said to be the one-to-one if the each B in Rm space is the image of at most one most 1x. This is very intuitive. Okay, let's see the left image first. Some kinds of the back point x, point output p here. There exists so many mapped points from the domain or the input space. Okay, what about this point? This point also have the so many input values from the domain space. So in this case, the transformation T is not the one-to-one mapping. What about the right image? Each output P, vector P, is derived from the just one sample X. So in this case, this is called the T is one-to-one. So in other words, the is T is one-to-one means there exists there is a unique solution or not. So what does it mean? Okay, we want to solve the ax equals b. So in this case, the sum for the arbitrary vector b, there is only single solution x from the domain, right? But what about the left image? There are so many output x for the each b. So this is related to the uniqueness question. Okay, so this is the concept of the onto and the one-to-one, right? So here is the example. Let's the T is the transformation whose standard matrix is the like this. Okay. The question is does T transformation T map the R4 onto R3? The first question is related to onto. Then, if the transformation is the one-to-one mapping, right? So yeah, here are two questions. So first of all, ax equals b is the okay. Let's do this color. Okay, with this matrix A, we can find the solution ax equals b with this matrix A, right? So in this case, okay, let's see the matrix A first. This is the echelon form, right? So this is the echelon form, and they have the three pivot position, right? So what does it mean? Okay, if we go back to the lecture 3.1 here, there was the theorem, like where is that? Yeah, here. So A has a pivot position in every row. It means that the equation has a solution, right? Right? So what does it mean? The ax equals b is the consistent in this case, right? In other words, the transformation T or the matrix A map the R4 space onto R3 space, right? Right? Why? Because there exists a solution. So in this case, the output and the mapping function will be looks like that, because the range of the output is exactly the same to Rm space. So in this case, it satisfies the onto property. And secondly, since the ax equals b has a free variable, right? Because we have a three pivot position, so x1, x2, and x4 will be the basic variable, but x3 will be the free variable, right? So in other words, there are infinitely many solutions. So it means that it is the left image case, right? So in other words, there is the no one-to-one mapping relationship. So in other words, T is not one-to-one case for this matrix A. Okay, so this is the concept of the one-to-one mapping. Here are two more theorem, right? Actually, from this week's lecture, there are so many theorem, right? So I guess you might have some trouble to follow each proof of the theorem, right? So it is really difficult. So it is hard to derive yourself. So but don't worry about that, because this is only theorem, so you can just remember what this theorem means, and then you can just follow the proof on the textbook. So actually you don't need to remember every proof, but please remember what this theorem means. Okay, let's see the first theorem. Okay, let's say there is the linear transformation T from the Rn to the Rm space, and then transformation T is the one-to-one. If and only if the T of X is 0, has a only trivial solution. Oh, by the way, do you know the meaning of the if and only if? Actually, most theorem has the statement something like that. If and only if. It is also called the IIF or IFF. What does it mean? This one satisfy this one, or this one satisfy this one simultaneously. So this is the meaning of the if and only if. Okay, let's prove this one. There's two possible case. If T is one-to-one, the equation Tx is equal to 0 has the at most one solution, right? Because there should be only one solution for this zero value, this zero vector. So in this case, the x is equal to 1. This is trivial solution, right? It's the only solution. Okay. The second case, if the T is not one-to-one, there should be the vector B in the output space that derive from the two different points from the X domain. Let's say that this is the input domain, this is the output domain, right? Okay, so for arbitrary point or the arbitrary vector B, if the transformation T is not one-to-one, there should be two different points. Okay, let's say this is the vector U and vector V. Okay, this is the vector B. Okay, in this case, transformation vector U is equal to B vector B, transformation vector V is equal to B vector B, right? And in this case, we can say that transformation U minus V is going to be TU minus TV, right? Because the transformation is linear, right? So in this case, this one is vector B minus vector B will be 0. right? So, but in this case, this is not 0 because u is now equal to v. So, in this case, transformation. Okay, let's say this is the new vector w. So t w is equal to 0. So what does it mean? The equation t x is equal to 0 has the more than one solution. More than x equals 0, x equals 0. They'll have another solution, w, right? So from these two statements, we can say that two conditions are both true or they are both false, right? So it means that this is the proof of this theorem. Okay. Okay, let's move on to the second theorem. So let's say there is the transformation T from the Rn space to the Rm space. Okay. So let's say the matrix A be the standard matrix of the transformation T. Then there are two sub-theorems. The first one is the transformation T map the Rm onto Rm if and only if the columns of matrix A spans the Rm space. Okay, let's prove this one first. So what does the meaning of the columns of the matrix A spans the Rm space? What does it mean? What does it mean? What is the columns of the matrix A? Okay, let's say matrix A consisting of the column vector something like this, right? So then in this case, the A times X is going to be X1 times A1 plus X2 times A2 plus Xn times An, right? So in this case, this value will be the coefficient of this linear combination, right? Then what is the span? What is the span? Span is the linear combination of these column vectors, right? Then when this coefficient makes this column vector of A spans the Rm space. What makes that? What makes that? For the arbitrary vector x, this column vector A can fill the whole point in the Rm space. Let's say this is the Rm space. This column vector linear combination of this column vector will make some point here point. But if the column vector A span every point in the Rm space, right? This is the meaning of this statement. Then in this case, this is the onto from here, right? So every possible point are in the Rm space. So this is the proof of the first theorem. What is the second theorem? So the transformation T is the one-to-one if and only if the columns of A are linearly independent. Okay, what was the linearly independent? Let's go back to the last lecture. What was the linearly independent? No. It was the section linear independence. Here, also linearly independent. If there is the only trivial solution of the AX equals 0, it means that x1 and x2 and xp is going to be 0, right? So this is the linearly independence, right? So if we go back to here, there is the columns of the A is a linearly independence when AX, this homogeneous solution, has a trivial solution. Well, when x is equal to 0, right? Then, what was the AX equals B? What was the solution of this non-homogeneous system? This is homogeneous system, right? What was that? The solution of the non-homogeneous one is the some arbitrary vector p plus some parameter lambda times the solution of the homogeneous one, right? So in this case, this is 0, right? From this one, so it means that solution of the non-homogeneous system is just arbitrary vector p, right? So it means that the solution of the AX equals B is the only single solution, or the exactly one solution. So it means that there is the one-to-one mapping between domain and codomain case. So in this case, we can say that transformation T is the one-to-one. Okay, so this is a two sub theorem. Okay, so to summarize, we can check whether transformation T is one-to-one or one-to by low reducing the matrix A. After low reducing the matrix A, if there is a pivot in every row, like this point, no, where is that? Yeah, here, like this one. If there is if there are pivot position in every row, then in this case AX equals B is consistent, so then we can say that this transformation is onto, right? So if the pivots in every row, we can say that this transformation is onto. Another one is if there is a pivot in every column, the transformation T is the one-to-one. Transformation T is one-to-one. So this is the definition of the one-to and one-to-one case. Okay. So your definition. From now on, we will talk about the geometric transformation. Actually, geometric transformation is just some particular transformation set that have some geometrical property. So actually, you don't need to remember this single geometric transformation. But if you understand how to say property or the action of those kinds of the matrix, you can easily understand the mapping property of the matrix A. Okay, first of all, let's start from the reflection. What is the reflection? Let's see the example here. If the matrix A looks like this, right? So what is that? Okay, matrix, we want to find the AX equals B. So this is a matrix A, right? So what does it mean? So because this vector x is the x1, x2, right? Then in this case, this matrix A transform this point onto the another vector space, another output, right? So for example, if we use this matrix, we can transform the original this image something like that. How? You can easily derive this. Okay, let's say this is the 1 by 1, right? So in this case, 1, 0, 0, negative 1 times 1, 1 will be the 1 times negative 1. So what does it mean? This point will move to here, right? What about this one? This is 0 times 1. Then 0, 1, it means that 0 times negative 1. So this point moved to here, right? So every point in here moved to here. So when you see the figure of this object, something like this, the output looks like this. So this is the reflection through the x-axis. What about the x2 axis? We can use this matrix, negative 1, 0, 0, 1. This is a reflection through the x2. What about reflection through the x2 is equal to x1, like this one? We can use this one, 0, 1, 1, 0. Why? Okay. This is the input vector x. So 0, 1, 1, 0. So it will be the 0, 1. So it will be 0 and 0. So then 0, 1. What about this point? 0, 1, 0, 1, 1, 0. So it will be 1, 0. So in this case, these two pointer replaced each other, right? So this is the reflection through the line, right? Then another one is the reflection through the this line will be this matrix. Reflection through the origin will be this matrix. You can do this one yourself, okay? And there is another geometric transformation, contraction and expansion, okay? So the horizontal contraction or expansion looks like this matrix, right? If the k is larger than 0 and less than 1, the shape of the output looks like this. If k is larger than 1, the shape will look like this. Then what about this? It make shrink or stretch the original 1 by 1 image, something like this and something like this, according to the k values, right? So this all images start from this original image, okay? Then there is the shear transformation. We already talking about the shear transformation in the last lecture, right? So using this one and this one, we can shear horizontally and vertically, something like that, something like that, something like that, something like that, according to the value k. Okay. Finally, there are projection transformation. If we use this matrix, we can just project the image as a line in x1 axis or y1 axis, something like that. Using this is a projection. So yeah. Okay, so this is the end of the chapter 1 in the textbook. We are now here, right? From now on, there are several kinds of the topics related to the linear algebra, but please remember it. We are just talk about the ax equals b or ax equals 0 problem, right? So from now on, we will do more practical solution in the matrix domain. So something like the LU decomposition, some Graham-Schmidt or the Cure decomposition or the eigenvalues or eigen decomposition. Okay, so those kinds of topics will be not easy, but this is the based on the first chapter. Okay,